Hey guys, we are registered as Desert Eagles, and our problem statement is microphone array based direction of arrival for gunshot detection. This is a software category, and you can see our team ID here. And essentially, we are proposing a comprehensive gunshot detection system which uses both hardware and software solutions in order to determine when and whether a gunshot is has occurred using an omnidirectional array mic or a mic array. We are planning to have 6 mics for this array, which will enable us to detect sound in three dimensions and ensure that a gunshot can be determined in terms of its type and where it's coming from. So we now move to the idea title and what we plan and what our system or solution is. So it is called Sarvaj, and it is a comprehensive gunshot detection system. The main software processing behind this system here is a sound classification and localization algorithm, which involves DSP techniques, statistical analysis, using of machine learning models, which such as a convolutional neural network, and a vector calculus system of linear equations to determine the localization or the direction of arrival of the gunshot. So, our proposed system is intended to perform across diverse terrains and also accounting for wind noise conditions using denoising algorithms, and we intend to scale up this proposed system into a network of multiple detection units that cover a large area. So we now move into the process flow for the system. So we have two main process flows. One is a hardware process flow and a software process flow. So the hardware flow involves the mic array itself, which moves to the analog to digital converter to be converted into a digital signal system. And this will be fed into an FPGA at the final implementation level, which will provide the output through its computing and the stored algorithms in its hardware onto a graphical LCD display. We can also move into further output systems in the future. The software process flow is very simple. We have two main parts of this, the classification and the localization parts. So when we get the sound signal input, we pre-process it and denoise it, and then move into a multi-level denoising algorithm, which uses frequency filters such as ABFF. Then we extract the features of the sound signal using a Mel's frequency substrate coefficient method or approach to create a spectrogram. This spectrogram, or an image-based graphical representation, is fed into a convolution neural network or CNN or a pre-trained model, which will check whether the visual components of the spectrogram resemble a gunshot. If so, then we move into a statistical and ML-based classification using CNN and determine whether and what type of gunshot it is, whether which gun has fired it, such as for example an AK-47, a machine gun, or a sniper, etc. After this classification is completed, the same input signals from the different mics are fed into the sound localization algorithm, which will determine the time difference of arrival and direction of arrival to accurately estimate where the gunshot has come from. Both the classification and localization data is fed into our response analytical systems, which will be integrated with this system in order to respond to the location and the detection of a gunshot accurately. So now we move into the implementation of this system. We have shown some pictures here based on our implementation so far. So now we will move into a detailed explanation of how exactly we have moved to this implementation. Now, coming to the process flow of this project, we will focus on the software flow first. Now, since we cannot model a gunshot directly, as we have no access to such facilities, we have decided, for the purpose of this initial simulation, to simulate the gunshot inputs at each mic using mathematical algorithm. And for this, we have used MATLAB in order to model the parameters using polar coordinates, including parameters such as temperature and humidity for modeling the attenuation accurately. We have used audio signals in the .wav format, and we've also modeled the speed of sound and accounted for the mic array positioning as a triangular mic array situated in an equilateral triangle with the 47 centimeter distance from the centroid to each mic vertex. We have calculated the time delay between each mic for a particular signal source and calculated the loudness based on the attenuation modeling. And we have created and saved 3 WAV signals using zero padding. After doing so, we normalize these signals and we input them into the localization algorithm, which uses a formula we have obtained through our literature review in order to create a system of linear equations that enable the localization, determine the direction of arrival using the phi and theta values for azimuth and elevation. For this particular initial simulation, we have used a triangular mic array which does not have z-axis processing or vertical processing capabilities. Therefore, this particular mic array cannot determine or detect signals that come from above it in terms of z-axis or elevation theta. Therefore, for now, we have used only modeling for r and phi, which is the azimuth angle. Thus, this signal or this processing allows us to determine the direction of arrival of the gunshot and accurately place the source of the sound. Moving to the detection and classification part of the algorithm, we have decided to use Python for this initial implementation along with Google Colab and in Jupyter Notebook. This allows us to access Google Drive for our storage and allows us to use both TensorFlow and Keras accurately and efficiently for our model building. We have used an Atom optimizer to adjust the learning rate of the model, and we have gone through the flow of using a pre-trained model, validating it, training it, and saving it, and using it for the detection. We've used a MobileNet model for the detection algorithm using Librosa audio processing library and OpenCV image processing library. We've used scikit-learn for splitting the dataset and test set building. And we've used the method of transfer learning, which freezes model layers in particular use cases to save computational efficiency. And we've plotted the training algorithm using 50 epochs, and we've used the Mel's frequency septal coefficient spectrogram, which to display the audio signal as an image output for the model to use to predict its results. This model using MobileNet detects whether the gunshot has occurred and analyzes accurately whether or not a given signal contains a gunshot occurrence or not. For the classification part of the algorithm, we have used the same flow as detection using Python and Google Colab. However, the main difference here being for the training and saving, the model we've used is a convolutional neural network model called VGG19. It again uses 50 epochs with a batch size of 32 and uses a model of the process of transfer learning and training in order to train as to whether what gunshot it is and which weapon type has fired the gunshot. So again, this model uses the image processing technique of a spectrogram using MFCC, which the model uses to predict and play with the results in order to determine what the gunshot type is. You can see the training process here and the training validation and accuracy being displayed for both detection and classification. And we also see the evaluation of performance and the accuracy of the prediction. In this example, we can see that the prediction is accurate for the given gunshot training, the gunshot occurrence that has happened. For the hardware, we have used a mic array with 3 mics for the initial implementation. We've used condenser mics for the initial implementation again because we intend to use better mics such as MEMS mics for the future implementation as we proceed with the project. Before we implement the initial array, we first test the mics that we have selected using a preamplifier, which we test using a 3.5mm jack connected to a laptop processor. So we model the gain for the sound inputs that we generate to make sure that the gain for the preamplifier is modeled correctly before usage in the processing algorithms. We now move on to the mic array, which has 3 condenser mics in a equilateral triangular setup with 120-degree separation and 47 centimeter distance between each mic and vertex and the centroid. This is connected to an LM328 quad op-amp preamplifier, an Arduino Uno board, and a SD card reader for processing of the input signals accurately. We have also used a tripod stand to stabilize the mic array in order to ensure that vibrations are reduced and the mic input signals are left undisturbed. The obtained input signals from the mic array are then stored in an SD card in the laptop in order for further processing using the algorithm that we are using. Just to show this hardware implementation using the obtained input signals from the SD card, we have used Audacity, an audio processing software, to highlight the time delay between each mic input. Since the source is not is at different distances between each mic in a real-time 3D simulation, and so the time delays are displayed using Audacity, and the Mel's frequency substral coefficient spectrograms are also displayed for each individual signal, where we can see the time delay between mic 1, mic 2, and mic 3. This very same image information using the spectrogram and the signals and the time delay are used for the localization and classification algorithm. Moving to the final implementation of this project, it will involve having a 6 mic array with 6 sound signal inputs and an integration of all the Python and MATLAB codes into one single code that will be moved into an FPGA system using a hardware description language. This integrated approach will be streamlined and efficient. Now moving on to the future and final implementation of this project. Coming to the strategies to overcome these hardware challenges, we intend to appropriately and carefully select an FPGA with the compatibility of the ML algorithm implementation in mind, and also perform a little bit of material science in order to ensure that each component of the hardware implementation is durable for all test cases. Moving to the impact and benefits of the current project, we expect that this project will be used by security authorities, the military, and also wildlife authorities for anti-poaching initiatives. And because of this, proposed device has the potential to dramatically improve the security and surveillance systems with minimal cost addition and implementation and installation. So the project has huge impacts both in the security and ecological space, and we intend to improve such said security measures and systems using our addition to this technology. We, Desert Eagles, thus intend to revolutionize the security systems of India using this project statement and our implementation, Sarvaj. Thank you.